My name is Anthony Semt, and this is Physics Lab 4, Oscillations. In this lab, we use Tracker to observe the motion of a spring moving in two dimensions, x and y. Then, I created a computational model to visualize the ideal motion based on the energy principle. And then I took those two models, the observed data and the model, and compared them and figured out why are they different. So some important equations, principles, and formula used in this experiment were Newton's second law, which we all know states F net equals dp dt. I also showed the velocity update formula because that's pretty important to this lab. Next, we have Hooke's law, which is all about springs. So we have negative Ks, where S is the magnitude of the length minus the rest relaxed length. Next, we have the energy principle, which is arguably the most important part of this lab, which states that the change in energy is equal to the sum of the change of those individual kinetic and potential energies. Here's the equation for kinetic energy and our two potential energies, spring and gravity. And these equations are derived from those force equations that we've worked with in the past. Next, we're going to look at the observed data just briefly because this is a long video. As you can see, the spring is going all over the place, and it is important to note the quality of this video. So here's some room for error and in the provided video. So the video provided has some room for error in the computational model and my analysis because of all the uploading and downloading and analyzing in Tracker, the frame rate and the quality of the video just deteriorated significantly and I couldn't figure out a way to fix it. So the oscillation period does not reflect actually what happens from what I saw in Tracker, and this is going to throw off the spring constant and the relaxed length. So to compensate, I referenced the pre-lecture video number 52 and used that as a basis for my data. So finding K and the relaxed length, I used this equation to calculate the spring constant or the spring stiffness, and I used this equation to calculate the relaxed length. Now into my code. First, I set the mass of my ball, or weight, its initial position, which I got from Tracker. Initial velocity was at rest, and then we started at time 0 with that time step. Next, I calculated gravity. It's 9.8, always is, on Earth. Then we have the spring constant, which I showed you the equation for a moment ago. Same thing with the relaxed length. And now I set up my U spring calculation by establishing what L, L hat, and S are. Next, I calculated kinetic energy and potential energy, as well as total energy, using those equations that I showed earlier. And then I just set up an initialization step, calculated F net using F spring and F grav, and then velocity update formula, position update formula, to calculate the new position and velocity of the ball. Once again, I recalculate those components of the spring force, the L hat, and the S. And then I calculated all those energy changes. So basically at this new position, how have those energies changed? Now here is the computational model I come up with in GlowScript. And I sped it up a little bit here, but you can see that red ball is staying very, very close to that blue ball. The red ball is what I calculated, or is what I observed rather, and the blue ball was the model data. As you can see in these graphs, they're very, very close, and those differences can be due to a number of things. I estimate that it's probably dissipative forces and drag and things like that. Minor real-world things that we typically ignore in these calculations. So what does all of this mean? Well, it means that the energy principle was followed. The change in total energy, which as you can see is that orange line, is constant at 0. Which is what we predicted at the beginning. We figured since there's no work going on this spring, we're not doing anything, we're just letting it go, there shouldn't be any delta E. However, you can see that there's a lot of wavy lines in there. That's the components of E. And at each point, they're canceling each other out. So we have a net 0, kind of like how we had net forces. We have net 0 energy change. And this is in keeping with the energy principle. As you can see, these are adding up at each point to equal 0. Next, we have our oscillation periods and kind of some more propagation of that original error. As mentioned, the video caused some error. So again, I based these numbers off of pre-lecture number 52, and then I did some, using those original equations that I showed at the beginning, I did some math to try to figure these out. As you can see, the oscillation periods are fairly similar, but even those small differences, that 1/10 of a second or so, led to a frankly large change in the stiffness and a very large change in the relaxed length. So I opted to choose the y direction for this experiment because there was a lot more motion in the y direction than the x direction from the observed data. That's all I have. Thank you for watching.